Welcome to Quantum Field Theory, Lecture 17. In this lecture, I will continue the discussion of the propagator in scalar field theory that we started out in the last two lectures. Recall that in Lecture 15, we introduced the full propagator as the path integral of the two-point function weighted with the full action rather than just the perturbative action. We were able to expand this expression to in perturbation theory, so that we find that to first order in perturbation theory, the full propagator G1 is given as the free propagator and the correction term, where the correction term involves the expectation value of the two-point function and the action, which in our case is a four-point function of the field. Similarly, we can use the first order perturbative expression for the partition function, which is just the free partition function minus the expectation value of the interaction part. In this lecture, what we want to do is we want to discuss the perturbative propagator given in equation 17.2, as well as discuss resummations of this object. The first order correction term is given as the expectation value of this form here. And if we plug in the explicit form of SI, we find that it's given as an integral over Euclidean 4 space y times phi of x, phi of 0, and phi to the fourth power of y. We can use Wick's theorem to expand this expectation value in terms of two-point functions of the free theory. So we find that if we keep track of the contractions, which gives us this vector 12 here, that this expectation value on the left-hand side is given as an integral over 3 propagators. We can use the known form of the free propagator G free, and we find that this propagator is the propagator from x to y, so it's x minus y. This propagator is y minus 0, so it's just G free of y. And lastly, we have a propagator that ends up at the same point where it starts, so this just gives G free of 0. We can use the explicit form of the free propagator that we wrote down in equation 16.2. And we can use a representation of the delta function, which is just the integral of the exponent of I y dot p minus k. And if we do that and plug it into the previous equation, we find that in the 0 temperature limit, the expectation value that we wrote down in the last slide is given as 12 lambda times G free of 0 times an integral that is of this form. So taken together with the leading order term, we find that the first order perturbative expression for the propagator is given as the free propagator and the correction term that we just evaluated. We can simplify this expression by realizing that both of these expressions involve integral over k space times an exponential, and then an integrand here that is purely a function of k. Because this form is in the form of a Fourier transform, we can again write down the perturbative result in momentum space, where the momentum space is again indicated as a tilde, where G1 in momentum space is just given as the free propagator in momentum space, and the correction term, where G free of 0 is just a constant. We have calculated G free of 0 in lecture 15 in dimensional regularization. The explicit form of the expression is equation 15.16. And as such, we know that what that constant is. And if we look at this, we can say that, okay, this expression given in equation 17.8 kind of looks like the start of a geometric series. We can verify that this is indeed the case by actually going to higher order in perturbations theory. So calculating G2, G3, and so on and so forth. And we find that besides other terms, there's always a corresponding term that really sort of completes a geometric series as is indicated by these first two terms here. So what we find is that the full propagator in momentum space g of k is given by an expression where we summed the geometric series indicated by the first two terms here, plus correction terms that start at second order in perturbation theory, because the first order in perturbation theory, resumming the geometric series is exact up to order lambda. While it is more complicated to write down the higher order expressions than the leading order result for the propagator, we can nevertheless write down the full propagator in a form that's indicated by the last slide, except that we allow for an arbitrary function of k here in the denominator. We call this function pi twiddle, and just comparing with the last slide, we find that to lowest order in perturbation theory, pi twiddle is just given by 12 lambda times g free of 0. So it's just a constant. We call pi the self-energy for the scalar field phi. And I will just note that the self-energy is a very important object in quantum field theory, and it contains an enormous amount of information, some of which we will come back to in the later lectures. So now let's inspect this first order perturbative result of the self-energy. All we need to do is we need to plug in the explicit form of the constant g free of 0 that we found in lecture 15, specifically equation 15.16. If we plug this in, we find that the first order perturbative self-energy is given by this combination here, where IB was a thermal integral that we've defined in the previous lectures. Note that this result for the self-energy is divergent if we let the regulator epsilon go to 0, because we have a 1 over epsilon term here. And I should also say that the way that the self-energy appears in the propagator is always in conjunction with an m squared. So let me just go back to the definition of the inverse propagator. We always have m squared plus pi twiddle. So really sort of that is the important combination to consider. Once we realize that, we can realize that m squared is just another parameter in the Lagrangian. There is no a priori reason that the m squared must be the physical mass of a particle. It can just be a particle parameter. And as such, we can add a counter term to m squared, similar to what we have done with the cosmological constant. So at the end of the day, what we do is we replace the parameter m squared in the Lagrangian and write it as m physical squared plus delta m squared, where we expect delta m squared to be divergent and canceling the divergence we found in the self-energy. So what we can do is we can renormalize the combination m squared plus pi by choosing the counter term for the mass accordingly. And in ms bar, the form that suggests itself is to just cancel the 1 over epsilon term that we had in the self-energy pi of 1. So once we do that, we find that the combination m squared plus pi 1 is finite, and it's given by the expression in 17.15. And we can write this as m physical squared plus the first order renormalized self-energy, so just this combination of these two terms, plus of course higher order terms. Note that because our counter term here is order lambda, there are in principle terms in this combination that are divergent, but those are formally of order lambda squared or higher. So in perturbation theory, we don't have to worry about those. We would have to worry about them if we were aiming for a result that is accurate up to second order in perturbation theory. And if we do so, we would have to include a second order counter term as well. Let us now inspect what the physical interpretation of this renormalized mass will be. To that extent, let me remind you that in lecture 16, we found that the pole of the analytically continued propagator corresponds to the mass of the quasi-particle. So this is a physical object, and we can do the same. We can try to do the same now for the expression of the perturbative propagator that we discussed. So let's do this exercise now for the full propagator 17.10. To first order perturbation theory, if we analytically continue by replacing the Euclidean form momentum with the Minkowski form momentum, we find that the propagator has a pole located at k naught squared is k squared plus m physical plus the renormalized self-energy to first order perturbation theory. And that means that the quasi-particle mass that this first order perturbative propagator describes is no longer just given by the parameter m, or m physical for that matter, in the Lagrangian. Instead, it's given by some effective mass, that's the combination of m physical plus pi. And we can write down the effective mass of the particle as the combination of all the terms that we have in this expression here. Going back to this expression here, note that at first glance it looks like the expression for the effective mass is actually renormalization scale dependent, because there's an explicit mu here in this logarithm. It also seems like it's temperature dependent because there is a temperature appearing in this function IB here. Let us now discuss these two dependencies. Let us first concentrate on the zero temperature case. So if we eliminate the temperature dependence because the function IB at zero temperature is just zero. And we find that at zero temperature, the effective mass squared is just given by this combination here that includes the term from the renormalized self-energy. Since the quasi-particle mass can be measured, at least in principle, it cannot depend on an arbitrary scale mu bar, because this is a physical quantity is measurable. It can't depend on something that we can choose at will. That's not possible. So the only way out, since there's an explicit dependence on mu in the expression we found, is that some other quantity must cancel that dependence here, so that in the end of the day, the dependence on mu bar in m effective just drops out, and we can encode this information by saying that the derivative of m effective with respect to mu bar is zero for all values of mu bar. The way that we can engineer this is to say that the parameter m physical in the Lagrangian must depend on mu bar. If you do this, then plugging this back into our requirement that the effective mass has to vanish, we can derive this expression with respect to mu, and we get a consistency equation that just says that zero has to be the derivative of m physical times a contribution, and then there's a term that comes from the explicit derivative of the logarithm. Since this is an expression that is meant to hold in perturbation theory, in addition to just do the derivative, we also have to expand in powers of lambda, the coupling constant. So to lowest order in lambda, we find that the derivative has to be canceling this term here on the right-hand side. So this derivative of m squared with respect to mu is order lambda. And if we do this, then the term that we have not written down in this equation is order lambda squared. That's consistent with neglecting contributions that are order second order perturbation theory or higher. So what we find is that in order for a measurable quantity, the measurable quasi-particle mass, to be independent on an arbitrary parameter, mu bar, the Lagrangian parameter m physical has to depend on mu. This implies a dependence on mu that's non-trivial. And in the lingo of quantum field theory, what this means is that the mass is said to be running. So the mass parameter runs. We'll come back to this once we discuss, in particular, the renormalization group in later lectures. For now, let me discuss a second special case, which is the case where I set the parameter m physical in the Lagrangian to 0. And I keep the temperature dependence in this case. So what I find from the expression for the effective mass is that m effective is now given by the square root of this function IB. Since IB is evaluated at 0 mass, we can use the result that we have found before, 15.18, and we find that this effective mass is just given as the square root of lambda times t. The good news is that the effective quasi-particle mass in this case is independent of mu bar. That's a consistency check, but it depends on the temperature. It turns out that this is a real physical effect. We call this the in-medium mass because even if the quasi-particle is massless at 0 temperature, the interactions with the medium give the particle a mass, and this is an effect that can be physically measured and is important in many media or systems of physical importance. In fact, it is true that the in-medium mass, meaning the temperature-dependent mass for the quasi-particle, is generically unavoidable for any value of the physical mass, even though we sort of choose a value where this is particularly simple. And we'll sort of have this effect even if the physical parameter m physical is non-vanishing. And this concludes the lecture.